Hi everyone, I'm Prachi Garg from IIIT-Hyderabad and I'm here to present our work Multi-Domain Incremental Learning for Semantic Segmentation. At the center of our work lies this idea. Can a semantic segmentation model continuously learn novel domains without forgetting previous knowledge? So let us take an autonomous driving car and we want this model to incrementally learn novel geographic road scenes as and when the data comes in. In the first step, the model learns on this domain. In the subsequent step, the model is incrementally trained on a new domain. As the model is continually adapted on the new domain, it forgets the previous knowledge. This phenomenon is commonly known as catastrophic forgetting in continual learning. A naive way to solve this problem would be to train and store separate models, one for each domain, and deploy them when the city changes. A second way would be to store all the datasets and train a joint model every time new data becomes available. Both these solutions are highly inefficient because they involve high storage and computation costs. So we define multi-domain incremental learning as incrementally adapting to new domains while preventing catastrophic forgetting on previous domains, given that previous domains' data is not accessible and there is no restriction on the label spaces of these domains. In continual learning, plasticity refers to learning new knowledge, whereas stability refers to retaining old knowledge, and there is always a trade-off between the stability and plasticity of a model. When learning real-world road scenes from diverse geographies, there is a possibility of having non-overlapping label spaces. So in addition to the domain shift, there can be a semantic shift, as illustrated in this figure. So our objectives can be outlined as attaining an optimal stability plasticity trade-off, dealing with both domain shift and non-overlapping label spaces, learning without relying on old samples, and aiming for high knowledge transferability. Incremental learning methods can be classified as replay-based, regularization-based, and architecture-based. We propose a dynamic architecture-based solution wherein the network is reparameterized into domain-specific layers and shared layers. The shared layers are domain-invariant and capture homogeneous semantic features common among all domains. On the other hand, the domain-specific layers are responsible for capturing heterogeneous dataset statistics of their respective domains. The model being trained in the current step is denoted as empty. This model has access to the current domain's data as well as the previously trained model MT-1. The different colors denote different layers in our architecture. The orange layers are specific to the previous domain and are freeze during training of the current domain. The blue layers are specific to the current domain and are trained only on a cross-entropy loss for the current domain. The green layers are shared between both the domains and they are trained on a combination of the cross-entropy loss as well as a domain-adaptive knowledge distillation loss. We use differential learning rates and an intuitive initialization strategy to achieve a good stability plasticity trade-off. In the evaluation phase, the model can be thought of as having multiple domain-specific paths, and for evaluation on any domain DT, the corresponding domain-specific parameters get activated in the forward pass. Next, we show experiments on one of our settings. In the first step, the model is learned on Cityscapes. As the model is trained on a new domain BDD in step 2, the Cityscapes performance undergoes a drastic forgetting. Similarly, in step 3, when the model is learned on IDD, both Cityscapes and BDD performances undergo a severe drop. Our model is able to mitigate this forgetting by a significant margin. Here we show the class-wise analysis for the Cityscapes domain after it has been trained on BDD. It can be seen that the model mitigates forgetting for safety-critical classes such as person, rider, truck, bus, motorcycle, and bicycle and can be very useful. Here we show some qualitative analysis. As the model is trained from Cityscapes to BDD, the latent space representation of Cityscapes gets distorted. But our model is able to preserve this latent space. We also compare the two scenarios for multi-domain incremental learning. In the first scenario, there is a domain shift but the label spaces are fixed. In the second scenario, there is a domain shift as well as a semantic shift. Here are some of our main results. The forgetting is indicated in red in brackets, and it can be seen that our model mitigates forgetting equally well in both the cases. We also study forward transfer and domain interference in these two cases, and more results can be found in our paper. Our work lies at the intersection of continual learning, semantic segmentation, and autonomous driving research, and will serve as the first real-world benchmark for domain incremental semantic segmentation. We hope to see you at the poster session. Thank you for listening to us.